Let's dive right into this explainer. Today, we're going to prove that those abstract, messy, mathematical equations you see on chalkboards, they're actually secret codes for predicting reality. If you've ever stared at a jumble of algebra and thought, come on, when am I ever going to use this? Well, you're definitely going to want to pay close attention. We're decoding the invisible architecture that governs literally everything around us. Picture this. You're standing in a field on New Year's Eve, looking up at the sky. A firework shoots up, pauses for just a split second, and then beautifully explodes. But how exactly do the engineers know precisely when and where that explosion is going to happen? I mean, how do they ensure it bursts at the exact right height instead of just crashing back down to the ground? Spoiler alert, it's not guesswork, it's math. And the answer lies entirely in the parabola. This is that invisible architecture we're talking about, the curve that governs everything from a rocket's launch to its absolute peak down to its eventual landing. A parabola is just a perfectly symmetrical, U-shaped curve. It's basically the visual fingerprint of a quadratic function. So whether you're mapping the physical trajectory of a falling object or, say, tracking the financial trajectory of a massive corporation, you are looking at a parabola. So here's our roadmap for today's explainer. We're going to start with the shape of reality, explore the three forms of quadratics, learn how to find the maximum peak, predict the landing, and then wrap it all up with the bottom line. All right, part one, the shape of reality, launches, peaks, and landings. Let's get right into it. Think about the launch phase for a second. We have our standard form equation. Height equals negative 3d squared plus 11d plus 4. At the exact moment a rocket fires, before it's moved forward even a single inch, its horizontal distance, our d variable, is completely zero. So if we just plug 0 in for d, those first two terms, poof, they just vanish. We're left with exactly 4. And that tells us instantly that our rocket is firing from a starting height of exactly 4 meters. Standard form is absolutely perfect for finding that starting line. Moving on to part two, three forms of quadratics, your mathematical toolkit. Standard, vertex, and factored forms are really just different lenses to view the exact same event. We just saw how standard form easily reveals that starting point. But what if we want to know the maximum height? Well, then we shift to vertex form. And if we need to know exactly when it hits the ground, we shift to factored form to find those landing points, or x-intercepts. It's all about knowing how to switch your mathematical lens to see the specific detail you need. Which brings us to part three, finding the maximum peak by completing the square. Okay, so to get from standard to vertex form, we use this really clever procedural trick called completing the square, and it involves three very specific logical steps. First, you isolate the squared and linear terms by factoring out the leading coefficient. Next comes the mathematical magic. You have the middle term, square it, and then both add and subtract that exact value inside your equation. This keeps everything perfectly balanced. And finally, you just condense it all down into a neat, perfect square. Let's actually apply this to a real firework. Step 1. We factor out the negative 4.9 from our t-squared and 10t terms. Now for step 2. We take half of negative 10, which is negative 5, square it to get 25, and then carefully add and subtract that 25 right there inside the parentheses. Now, we haven't changed the actual underlying value of the equation, right? Because adding and subtracting 25 is basically just adding 0. But we have fundamentally changed its structure so we can build our perfect square. So now we simplify the whole thing. We pull that subtracted 25 out of the parenthesis by multiplying it by our leading negative 4.9, which gives us a positive 122.5. Add that to our starting 1.5 and boom, we get 124. The equation is now completely in vertex form, revealing that our peak sits exactly at the coordinates 5 and 124. Translating that back to reality, our firework hits its absolute maximum height of 124 meters at exactly 5 seconds. We literally just found the perfect explosion point. But hey, watch out for a super common trap here with vertex form. The standard formula is inherently written as x minus h. That means the x value of your vertex is always going to have the exact opposite sign of the number inside that factored parenthesis. If the parenthesis says minus, your actual coordinate is positive. If it says plus, the coordinate is negative. It trips people up all the time, so definitely keep that in mind. For example, if you have a minus 6 inside the perfect square, that yields a positive 6 for the true x-coordinate. And because it's positive 6, it shifts our entire parabola 6 units to the right. Meanwhile, that negative 28 on the outside, that stays exactly as is, telling us the y-coordinate shifts straight downward by 28 units. So our lowest point, our vertex, rests precisely at 6, -28. All right, moving into part 4, predicting the landing, where it hits the ground. So we've launched, we've peaked, but eventually gravity always takes over. To find out exactly where an object hits the ground, we just have to recognize that the ground literally means a height of 0. So we set our entire equation to 0. From there, we break out the famous quadratic formula, carefully plugging in our a, b, and c values. By calculating those roots, we find that our rocket lands exactly 4 meters horizontally from where it fired. And of course, we just throw away the negative result because, well, unless you've got a time machine hiding in your garage, you really can't travel negative distance. And finally, part 5, the bottom line, from gravity to profits. Now, what if I told you that the exact same math we just used to launch fireworks can actually predict a massive $8 million business success? I know, it sounds a little crazy, but this invisible architecture, it genuinely doesn't care if you're measuring physical altitude in feet or financial profit in dollars. It is the exact same curve. Let's look at a real-world business example. Say we have a standard form equation modeling the profit for a video game company. By just completing the square and converting that profit equation right into our trusty vertex form, we instantly pinpoint the absolute maximum peak of the entire business model. The vertex sits right at 7 and 8. In context, that means producing exactly 700,000 video games yields a maximum profit of $8 million. Produce fewer games, you make less money. Produce more games, your production costs eat up all your margins. Vertex form literally finds the absolute perfect sweet spot for the business. And you know, just like calculating a rocket's landing where the height hits 0, we can also figure out exactly when a business is going to crash. By setting that same profit equation to 0, we shift into factored form to find the roots. And this reveals that at exactly 500,000 games and 900,000 games, the profit drops to 0. Those are the company's break-even points. Step outside that incredibly specific parabolic window, and the business is suddenly operating at a total loss. So, we've seen how these simple equations, whether in standard, vertex, or factored form, really do hold the secrets to everything from physical flights to millions of dollars in corporate revenue. Mathematics isn't just numbers on a page, it's the underlying language of our reality. It allows us to predict, to optimize, and to understand the world around us. Thanks so much for joining me for this explainer. The only question left is, now that you can see this invisible architecture everywhere, what hidden patterns are you going to decode next?